Why there's so many strings on an instrument? How come the instrument looks the same but sounds so different? How do you make it sound so nice?
Hey Michelle, what is sound anyway?
Well, actually, sound waves in air are governed this partial differential equation. The second partial diffusion of y with respect to t is equals to kappa over rho times the second partial diffusion of y with respect to x. Now, can anyone solve this equation? I will give you 10 seconds. 10, 9, 8, 7.
There should be an answer to all the questions in the universe in this book. But I don't seem to be able to find anything here. My whole life has been a lie.
Maybe I can answer it.
But how should
Q, E, D. Quite easily do that.
Well, QED stands for Qua Era Demonstratum, and it does not apply here, little girl. But the solution is correct. Do you all understand now?
Prof, I still don't get it.
Prof, can you speak in English, please?
I can help you with that. Tunk. I shall attempt to explain to you the behavior of sound waves in a simpler way. Sound waves are longitudinal waves, which means the air molecules are displaced forward and backwards on the same axis along which the sound travels. The waves are single-dimensional from source to receiver, as I shall demonstrate now. This slinky represents the air particles between the source and receiver. As the source vibrates, the air pressure around the source changes and is transmitted like this. At times, it is echoed, and at other times, it is absorbed. It is usually the combination of the two, depending on the material of the receiver and the medium of transmission. In this case, the air.
Oh, this makes so much sense.
No wonder when you're further away from the source, the sound gets fainter.
Yeah, but how do you explain tones, music, and songs?
Yeah.
Professor Vicky, I need your help here. Well, music is produced by a vibration of musical instrument and propagated by air to a listener. The vibration behavior of a system with a single degree of freedom can be expressed in this form. The left side of this equation is the forcing function, and the right side is the resultant vibration. The solution to this system in the case of free vibration reveals that there exists a natural frequency of which propagate of square root of stiffness divided by mass.
Prof, again, can you speak in English, please?
What the professor is desperately trying to say is that if you make the object more flexible and heavier, you will reduce the frequency of the vibration. I was that you will understand, blowing the musical notes.
There is another way to visualize this. Observe this metal ruler. You can see the frequency of motion. Now, if I were to add some weight onto the ruler, like such, you can observe the new frequency of motion. It is quite obvious that the frequency of motion has been lowered.
Wow, this is so enlightening. So I'm guessing that the glass with the most water will produce the lowest note.
Hey, this is the C note. And this is the D note. Let me play a song.